Homework number 7 deals mostly with vector spaces and subspaces, and then special cases. So a null space of a matrix is a subspace of a vector space. And then we finally define linear combination. And then we talk about what it means to, what a span of the set of vectors is. And that we learned that the span of a set of vectors is always a subspace. So, vector spaces and subspaces. So, and defining vector spaces, what it does is we define this mathematical structure called a vector space, and it unifies very disparate structures, not structures, but disparate mathematical objects, and we see that they have something in common, and we define that commonality by calling them vector spaces. And it allows us to prove something for a vector space, that allows us to prove something for all these disparate, seemingly disparate objects. So it's useful in that, useful language. So a vector space is going to be a set of objects, and that collection of objects we call V. And for these set of objects, we define addition. Now, addition, we're used to a certain standard addition of vectors and so on, but we can define addition any way we want it. It's just some operation we define, where we take two objects, we add them, and we get a result. So addition can be more general than we're used to. And so this set of objects, first of all, is, so I'm going to list the axioms. And the first so many axioms have to do with this vector addition. Right? So we have for all elements, called them U and V, in our set, if you add these two objects, you get something that's in the set. This is called closure under addition. Hopefully that makes sense, right? If you take two objects of some type, you add them, you'd like to see the same type of objects. So for example, dot product of two vectors does not satisfy this condition, because you take the dot product of two vectors, you no longer get a vector, you get a number. So we would say that's not closed under multiplication, I guess. Two, and I'm going to make sure I list these in the order that the book does. We have commutativity. So for all objects, maybe I should just say for all over here. For all objects in our set, U plus V is V plus C. So that's commutativity. Third, we have associativity. So this is very familiar. If you know like the properties of real numbers and such, this should not be unfamiliar. Right? So it doesn't matter whether you add these vectors first and add it to U, or these vectors first and add it to W, right? That's called associativity. This is true with number addition as well. So this shouldn't be a foreign property. There is an object called the additive identity, right, or the zero, and here to be really careful, right, because if I talk about the zero vector, I'm just talking generic vectors. You're thinking, oh, this guy, this is the zero vector, right? Well, the zero vector depends, how we define the zero vector depends on how we define this operation and what kind of objects we're dealing with. So I'll show you examples of where the zero vector is not really zero. 0, 0. So there exists, let me write that. There exists a zero vector or additive identity. We're going to call it 0 anyway. Your book does so. Such that for all u's, right, u plus 0 is the same as 0 plus u, which is equal to u. And if you have just Euclidean vector space, right, the zero, the vector with all zeros is the zero vector for that space. Because if you add any vector to it, you get the vector, right? And 5. Would be the existence of negatives of these vectors. So additive inverses exist. So for each element in V, there exists the additive inverse of the negative of U. And this just says that if you take the vector and add it to its negative, you should get the zero vector out. So, I mean, clearly, Euclidean vector, right? It has a negative, namely -1, -2, -3. We added it, and you get the additive identity here. Okay, so these 5 axioms are what what mathematicians would call this object is a group under addition. Okay, it doesn't matter, but these 5 axioms talk about addition of vectors, right? It's all about addition. Okay, the next 5 axioms talk about scaling. So we're dealing with real vector spaces. So this means that we can scale or multiply by scalars. And these scalars are real numbers. So we're not dealing with complex numbers or something like that. So our scalars are real numbers. That's why we call them real vector spaces. And we have a closure property for scaling. So if we take for each scalar that is a real number, and each vector, if you scale that vector, you get something that's n set. This is called closure under scaling or scalar multiplication. And again, the way we define scalar vector multiplication depends on us, right? It doesn't have to be the standard operation where you take a vector and scale by a number. Right? This is the standard operation, scalar vector multiplication. But we can define non-standard scalars as well. Okay. 7th axiom deals with how the next 4 axioms will show we want the scaling to be well behaved. So, for example, we want a scalar times the sum of 2 vectors to distribute, yeah. So that's kind of what we expect, it's well behaved. And that's for all scalars and all vectors. 8. likewise, we should be able to add two scalars, so k and m are real numbers. And if you then scale a vector, that should be the same as scaling the vector by each individual number or scale, and then adding the results. So in a sense, this multiplication distributes over scalar addition. Right, and this is now, okay, this addition is the same as that addition. Well, this addition is defined for these vectors, right? This addition is the addition of real numbers, so they could be distinct operations. So here I'm adding numbers like I'm used to because our scalars are real numbers. But here, this addition could be weird. Yeah, it's a different operation in general. And then you have that for any two scalars, you can scale the vector u by m and then scale the result by k, and the same thing as multiplying the two scalars together and then scaling the vector. And finally 10. This just says that the number 1, the real number 1, times any vector should give you that vector. So these axioms are all about how scaling should behave in our vector field. We have closure 1, and then this guarantees that scaling is well behaved. All right, so I guess if you wanted to show that something, well, if you want to check whether some set of objects with addition defined on those set of objects, if you want to check whether it's a scalar field, what I would recommend is first checking these two. These are the kind of key ones, because they're also going to be important later when we talk about the subspaces. In fact, they're going to be the only thing that will really matter later. So closure under addition, and then closure under scaling. Right? Because if those two don't work, then one of those fails. Okay. So I would check those first. They'll give you most of the answers quickly. And then you can check whether the others fail. So let's start looking at examples. So the first basic example is just, Euclidean vector space. Rn. It's going to be denoted by Rn. I wish I could have left the, I should have written that on the slide. So this is the set of all vectors. You can write them in a row or a column. I'll write them in a column. We have n components, where all these components are real numbers. I'm going to have to. Are you guys comfortable with the symbol element n? So this just says xi is a real number. It's in a set of real numbers. And we're used to dealing with these, and this will definitely satisfy all the properties, right? We'll look at some other examples which may be more interesting. Then we have the set of matrices. So the set of all n by n matrices. This is the set of all n by n matrices. With real entries. That's going to be a vector space. So now matrices are vectors. Okay. And again, if you want to look at that example, go to your book. I think for 2 by 2 matrices, it goes to the axes. So we have another example, Pn. So this would be the set of all polynomials of degree n or less is another example. So it's getting less trivial, right? More interesting here. I guess I should say that AIs are real numbers. So polynomial over real numbers. That's more interesting. Maybe we'll go back to those. So let's look at a specific thing. So suppose we have a set of vectors, objects, I won't call them vectors yet, that look like this. So x and say 3x. This set, where x is a real number. So this set of vectors geometrically represents what? In the plane, what is this? It's a line of slope 3, right? So it's a line. We're going to learn that so is this a vector space with the standard operations? On R2. So we add vectors like we're used to adding Euclidean vectors, and we scale like we're used to scaling. So first of all, is this set closed under addition? So how would I show that? So this is closure under addition. Well, to show that, you have to show that you can take any two vectors of this type, add them, and get a result which is of this type, right? So what I would do is take two things that satisfy this kind of structure where we have the first entry is any real number, the second entry is 3 times the first number. Yeah, that's the qualifying kind of condition. So for example, the vector 1, 3 has to be in the set. It satisfies that structure. But the vector 2, 1 is not, right? Because it doesn't satisfy it. This would have to be a 6 to do this. So you're going to take two elements in the set, and then you're going to add them to see whether you get something that's in the set. Well, if we add these two vectors, and again we're using standard operation, we did vector addition. A plus B, 3A plus 3B. And of course now we're dealing with properties of real numbers, right? We can factor out the 3. And does this is this in B? Well, does it have that qualifying structure where, the first entry is anything, A plus B is some number, that's fine. And the second entry has to be 3 times that number. And it does satisfy that condition. So this is so we just showed that if you take any two vectors kind of coinciding with that line, you add them, you get something that's on that line. We stay in this space in our set. So this is closed under addition. Is this closed under scaling? To show that it is, you would take a scalar, a real number in our case. And these could be positive numbers, negative numbers, or zero. It's always important to keep in mind those three cases. And then we're going to scale this vector using the standard operation of scaling. So indeed, right, this is just some number, but the second entry is 3 times that number. So it qualifies to be in our set V. So it's indeed. And the rest of the axioms are annoying, but because they will definitely follow. But we'll learn that soon enough. So what is axiom number 2? Commutativity, right, of addition. So we have, I mean, this is silly, but you want to go through all these axioms. Because there's 2 different questions in your homework. One question is this a vector space, right? So you have to go through the axioms. The second question is something a subspace, which is going to take less work. After we and we'll define what subspace is. But of course, number addition is commutative, so and there you go. Right, and you go through down the list. What's the does there exist a 0 vector here? So this is commutativity works. Associativity will work, and again, I'm not going to go through this, but associativity will work. Does there exist a 0 vector? Sure, it's just a 0 vector. It's the origin. 0, 0. We already have commutativity, so there you go. That checks. And 5, what was the 5th one? Yeah, so the negatives exist, because for any vector of that form, we know that there exists an element in our set V, namely minus A minus 3A, right? If you'd like, 3 times minus A. If you add these, we know we're going to get the additive. And then we check the rest of the scaling properties. So, 6. Well, I should have called this number 6, right? No, that wasn't it. All right, so is this closed under scaling? We said yes. And notice what that means geometrically. If I take a vector and I scale it by some amount, either a positive, right? I can even scale it by 0 to get the 0 vector, or scale it by a negative to switch the direction of the vector. We always end up on the same line. So the 7th one was distributivity. So scalar times u plus v will give us this. So you take a scalar, take 2 scalars, no, 1 scalar, sorry, and take 2 vectors u and v, and you see that just by the properties of Euclidean vectors, don't know where to stop here because this is really easy. You're just like almost hand waving. Still want to go through all the axioms and make sure they hold. Number 10, 1 times a vector is that vector, right? The real number 1, scaling a vector should give you that vector. So all these are hold. So that's a really simple example of a vector space. Now, what if we take this line that's through the origin and we shift it? Right? We translate it upward or whatever, which is some direction. So you would get a line which is not through the origin. So for example, let's consider the set V. Set V where we have x, and this is 3x minus 1, right?
Sorry, Les, so in that example, you were just showing all the axioms were proven by that V equals x, or the vector x to 3x?
Yeah, the previous example I was showing that V is a vector space because if you go through all 10 axioms, which is a pain, I know, they all hold.
Okay.
And if they ask you for, is this a vector space, you should go through the axioms.
Okay.
So if y equals 3x minus 1, and so essentially what that says, that's a line. That's not through the origin. Well, this slope 3, sorry, whatever. This line has a slope 3. Trust me. Okay. So this will not be a vector space, right? Again, I would start with the closure properties. So is this closed under addition? So I'm going to take 2 vectors that have that qualifying structure that, tells you that you're in V. Add these 2 animals. By all the properties of real numbers we have this. So what's wrong with this result? Yeah, it's a -2 instead of a -1. So this no longer has the form where the first entry is any real number. The second entry is 3 times that number -1. It's -2. To make it more concrete, you can think of a counter example where you have a 1 and this would be 2. You take, like, say, 3, and this would be 8, right? You add this up, okay, and you see that this is no longer in V because if it were, if this is a 4, what would this have to be? Well, it would have to be 3 times 4 minus 1, but that's 11, not 10. So this guy is not in our set. Okay. So, and then remember the closure properties have to hold for all pairs of elements in your set. So as soon as you find a pair where the sum is not in the set, we found a counter example, and we say that the set is not closed under addition. So we can stop. It can't be a vector space. You can show that it's not closed under scaling either if you want for practice. Now, here's an so next we're going to look at an example of something which is a more interesting example. It is a vector space, but we're going to define addition and scaling in a funny way to show you how that we can get abstract. So consider our set to be positive real numbers. So our vectors are numbers. And define addition, I might even use a different symbol to make sure we don't confuse, but no, it's challenging. We're defining addition to be, so u plus v by definition is going to be u times v. 1. And we're going to define scaling. So here's scalar k times vector u, which is also a real number. Define this to be k, u to the k. So I want to show that this is a vector space. So number 1, is this closed under addition, right? So if you take any two vectors or positive real numbers in this case, and you multiply them, don't you get a positive real number? This is a positive real number. So you take two numbers, positive numbers, when you add them, you're actually multiplying here by definition, and you get a positive number. So our set is closed under addition. Yeah, we get something that's. And I'll go ahead and check 6. So if you take any scalar, and we define the scaling here to be the positive number raised to the power k, this is always defined. And do we get a positive number? Sure. I mean, if suppose k is positive, right? Let's say positive 2. Then you're just taking a positive number, we're squaring it, so you're going to get a positive number. Even if you scale by the number 0, that's u to the 0, that gives you 1. It's positive 0. And if you scale by negative 2, it's really u to the negative 2, but that's just the reciprocal of a positive number squared, so it's still positive. So these are all positive numbers. So we have closure. Under scaling. So number 2, commutativity, so u plus v, that's really u times v, and because we're multiplying numbers, this is the same as v times u, so that's v plus v. And that's for any two positive numbers, so that checks. Associativity, this stems from the associativity of, right, so let's define this. So here we have u plus, and then v plus w is really the product, right? And then, so then we say that this is the product of all, right? But then we know product is associative, right? But multiplying is associative, so this is u v times w. And this is then, we define that as an addition, strangely enough. And then this product, the way we define it. So associativity holds. Okay, so here's an interesting one. The existence of a additive identity. What do you think our 0 vector is here? What is it? Origin. Okay, so we want to have a vector such that u plus the 0 vector gives me u, right? But how do we define this addition? As multiplication. Is u times 0 1? No. I mean, is it equal to u? No, it's 0, right? So our 0 vector is not the number 0. In any case, 0 is not a positive number. So that would be qualified. Our 0 vector, additive identity, is going to be 1. take any positive number, plus 1, that's really u times 1, right? And we know that's here. So our 0 vector is the real number 1. And do we have additive inverses? We have nit, right? So what we want to show is that if you take any element in positive integers, you add it to something. This is really strange. It's negative as the notation goes. That should give us the additive identity, right? Which is we define to be 1. All right. And this addition is really the multiplication of those two. So what do you think u times what would give you 1? It's reciprocal. So our negative vectors, or the negatives, are really reciprocals of this. And that's always defined because he's a positive number. So the reciprocal is this. Only 0 doesn't have a reciprocal. So the inverses, additive inverses, are the reciprocals. All right. So then we have, that's it for the addition, the way we define it. So now we go to scaling. We already showed that this is closed under scaling. We're going to go into, so take 2 scalars, or no, 1 scalar, sorry, and 2 vectors. Our scalar field, our scalars are still real numbers, and we're going to scale this. Okay, so let's be careful, right? U plus b is u times b, and then scaling is the way you can find it, u our object to the power k. Because that's the way we define scaling. But then these are all real numbers now, so properties of exponents hold. Are you enjoying this abstract example? Good. All right, but now this is multiplication of numbers, so we define that as addition. I know this is foreign, but it's just, I wanted to show you that this can get fairly abstract if you want to play that game. And then u to the k, that's the way we define scaling. And so that property works. Right? Scalar, scaling the sum of 2 vectors is the sum of the 2 vector scale. So now we take 2 scalars and a vector. We add the scalars, scale the vector. Again, so the way we define this is that this is really u to the k plus n. But now these are just properties of real numbers where we know we can write this as u to the k times u to the n. And this product is how we define addition. And this is u to the k is our scheme. So that the others will too. So take any 2 scalars. And a vector u. Alright, so this is u to the n. And then scaling by k is u to the n the power k, and then properties of exponents. So this is nk times the vector, or scaling vector. So that property holds. And of course, number one scales correctly. One scaling the vector u gives us u to the 1, which is u. It's all these axioms. Wow, okay. So that's a weird vector space, right? I mean, this is really what? Multiplying exponentials, right? Exponentials are positive, and when you multiply exponentials, you're really adding the exponents. So exponentiation turns multiplication into addition. All right, enough of that. Okay, so maybe here's a quick example of something. Okay. So our set is the set of vectors. Or, sorry, I shouldn't call them vectors. This is a set of ordered pairs where the entries are real numbers, and we define addition. So this will be quick because this is not a vector space. So we define addition to be, say, x, y plus ab. We're going to define it to be the product. And exponentiation is going to be, I'm sorry, scaling is going to be the standard operation we're used to. Okay, so this is closed under addition. Well, yeah, I mean, this shows it. You take two ordered pairs, you add them in this fashion, you get an ordered pair. Yeah. This means we're defining the addition to be the following. Maybe I should just leave the word define there, because that's, by definition, that's the way we add these ordered pairs. All right. It's clearly closed, right? Let's see. Under scaling as well, because that's just the standard operation of scaling. So we have closure, but what about the zero vector? What do you think that would be? So that's axiom number. What's our zero in this vector space? I wish they called it additive identity. But well, it would have to be the vector 1, 1, the ordered pair 1, 1. Why? If we add these two ordered pairs, according to our definition, we're actually multiplying the components. That would be x times 1, and y times 1. So this serves as an identity, active identity. This vector plus that one gives you the original vector, x, y. That's our zero vector. What about inverses? Well, here's the problem, right? We have additive inverses here. Well, okay. Well, I would first guess yes, right? Because if I add this ordered pair with the ordered pair where we take the reciprocals of these numbers, by our definition of addition, we should be multiplying these guys. And we indeed would be getting 1 and 1. Okay? So all ordered pairs, real numbers, have additive inverses. Is that the correct conclusion? Because when I took the reciprocal of these entries, right, I was assuming that they were non-zero. Okay. So if I had, for example, the ordered pair 1, 0, that plus what, or let's say 2, 0. That plus what, right? When multiplying gives you 1, 1. I mean, when adding, so 2 times a half indeed gets you 1. But 0 times what gives you 1? And remember, this is our additive identity, or 0 vector. So, nothing. You know, this doesn't happen. So, not all our ordered pairs have additive inverses. So, this is not a vector space. Fails the fifth axiom. All right, that's good enough. All right, so what's next? Subspaces, right? So, what is a subspace? Don't erase 5, okay. All right, so subspaces. So first of all, we have W is a subset of a known vector space. So we know we're living in a vector space already, right? And what we're doing is we're just taking some of the elements in that vector space, not necessarily all of them. And then a subset then is, a subspace is then a subset, first of all, of a known vector space. And number 2, W is a vector space in its own right. Okay. So a subspace is a smaller, well, yeah, broadly speaking, smaller vector space living in a larger vector space. And a lot of the properties, so to show that something, a subset, is a subspace, right, you need to show that it's a vector space. And fortunately, because we're living in a vector space in the first place, a lot of the properties, or a lot of the axioms, 6 of them, 6 of the 10 axioms, are inherited from the bigger space, yeah, from D. So, but not all the properties are inherited. So you would have to show what are the properties which are not inherited. I mean, I have them listed. All right, so 6 of the axioms are inherited from the mother space. But axiom 1, so this is closure under addition, is not necessarily inherited. Axiom 4, my bad. Existence of 0 vector. It's not guaranteed that a subset will contain a 0 vector. 5, existence of negatives or additive inverses. Not necessarily. And finally, closure under scaling. So, all right. So you would want to, I guess, show you don't need to show the 6 of the axioms. They're automatically inherited by virtue of being W being a subset of the vector space. But these 4 are not guaranteed, so you have to show they're true. However, you can show that if you prove the closure properties hold, then these will automatically follow. So these 2 axioms are a consequence of these 2 holdings. So let's see why really quickly. So it's going to be enough just to show closure under addition and scaling to show that a subset is in fact a subspace, a vector space in its own right. Okay. So suppose closure under addition and scaling holds. So this means that for each u and v in W, we know that u plus v is in W, and then k times u is in W for the scalar k, for any scalar k. So how does this show that, let's say, the 0 vector exists? Well, -1 is a scalar, right? So -1 times u by closure under scaling is in our set. So I should say, take any vector u in W. Then because we have closure under scaling, -1 times scaling vector u is also in W. But then we have u and minus u being in W. So if you add these, right, this will be 0. And this is the same 0 vector as that's in the original, the mother vector space. So this existence of the 0 vector is guaranteed by these two axioms holding. And the negatives exist as well. Very good. Again, it's the same reasoning. This is a vector in W scaled by -1. That's guaranteed to be its negative. Anyway, that's short of it is that you just need to worry about these two axioms to show that something is a subspace. So let's see. Let's look at things. So let's look at a couple of sets which are not subspaces. So consider the set of all vectors that look like, let's say, A, B, and then A minus B plus 2. Right. So this is a subset of what known vector space? R3, right? So that's a known vector space. This is a subset. So some of the elements in that set, not necessarily all of them. And if you wanted to see whether this is a subspace, a vector space in its own right, we just check the two closure properties. So can you give me an example of a vector that's in W? Let's say, 1, 3, what would this have to be? 1 and 3, 0, right? Because this third component, the defining property is that the third component is the first one minus the second one plus 2. So this is in W. And let's say 5, 1. What would this be? 6. Right? So these are in W, right? Okay, and I should say the addition and scaling we use is the addition and scaling of the known vector space. So it's going to be standard operation. We add these using standard operations. We get 6, 4, and 6. Is this in W? How do we check? Well, if this is A and this is B, we would like the third component to be A minus B plus 2. But that's equal to 4, right? That's what we would expect to see if this result were in W, but this is not. So this is not in our set. So this set is not closed under addition. Therefore, it cannot be a subspace, a vector space in its own right. So W, not closed under addition, so not a subspace. And it won't be closed under scaling either. But as soon as one of the two closure axioms fails to pull, we know we don't have a subspace, so I stopped. Okay. Let's see.
I have a question. Could you just choose those numbers in the 1, 3, 0 to this vector? So you choose those randomly?
Yeah.
Okay.
And you have to be careful because I could have chosen randomly, and maybe it would have happened that if I add them, the result is bad as also W. But right, we're not saying that we take two maybe you're saying that maybe there is a pair of vectors in W. If you add them, you still get something in W, right? But it's not necessarily true for all pairs.
So if it randomly did have to work, we have to do the other one.
Yeah,
And that one.
well,
Or
Well, so you might then try a different counterexample, and maybe you would still get something in W, and then you try another pair, you get something in W. At that point, you should be thinking, hey, wait, maybe this is closed under addition. And then you want to prove that it is closed under addition more generally. And we'll look at that as well, how to do that.
So because 1 is 646 and 1 is 644 are not.
Right, so this is in W, right? If this is A and this is B, the third component has to be 4. Yeah, it has to be A minus B plus 2. So this is not. So this cannot be in W. It doesn't qualify. Okay, let's consider, let me go over there. So here's an example of something which, will be closed under addition but not scaling. So this is a set of all elements in R2 that such that X and Y are both positive or non-negative. Right? So for example, 3, 1 is in W, but 3, negative 1 is not in W, right? Because we were saying that you only qualify to be in here if you don't have any negative entries. So if I add in standard operations, if you try to think of a counterexample or whatever, you add these things with non-negative entries, you get something with non-negative entries, right? And so it doesn't matter which two elements you pick from W, you always get something that has positive entries for the sum. So you start thinking, hey, this is closed under addition, and you want to prove it. So how to prove it? You would take two arbitrary elements in your set W. So take an element, say A, B, and U, B, I guess. And so all I'm assuming about these two elements is that the A and B are both non-negative, and U and B are both non-negative. That's the only thing, that's all we can say. And when you add these,
Is this part of the other one?
I'm sorry.
Is the one that you're doing right now part of the?
Yes, that's, I'm continuing the example I started with. Because I'm showing that W is closed under addition. Well, okay, how do we check whether this resulting sum is in W or not? Well, you have to, what would qualify you would be that your entries are not negative, right? So since A was not negative and U is non-negative, then A plus U is not negative. Because you're adding two non-negative numbers. And likewise for B, because it's non-negative because B and D were non-negative. So this is definitely in W. So we say that W is closed under addition. So what about scaling? Is W closed under scaling? Does anybody know what this looks like graphically, the set W, or geometrically? What is this? And if you drew in the XY plane, this would be the first quadrant, right? With the positive, or not, yeah, the axes. That would be graphically what that means, and it goes on forever. So you see why maybe this would be closed, this set would be closed under addition, because if you take two vectors, where both components are not negative, if you add them, right, you get something that's still pointing in the first quadrant. So you see why that the set would be closed under addition geometrically. I have a sense of what would happen. But now, what goes wrong with scaling? Well, imagine you have a vector, and you scale it. Remember, you can scale by positives. If you scale by positive, you still end up in here. You can scale by 0, and if you scale a vector by 0, here you get the origin, which is acceptable, right? 0, 0 is in W because it qualifies. Its entries are not negative. But you also have to always keep in mind that you can scale by negative numbers. So if I take an element in the set and I scale by a negative number, the vector flips direction, right? So now it's out of the set. Okay. So we have, if I take, so here's a counterexample, right? If I take scalar -1, say, and vector, say, 1, 2 in W, and I scale, I get something which has negative entries. So this is not in W. So even though our set is closed under addition, we see by this counterexample that W is not closed under scalar multiplication. So W is not a subspace. Okay, next example. Similar, but this time I'm gonna, if you were to try to cook up an example of a set which is closed under scaling but not addition, I would be thinking something like this, right? So if I take a vector that's pointing first quadrant and I scale it by positive, 0, or negative, I would still end up in the shaded region, right? So you expect this kind of set to be closed under scaling. But not under addition, right? Because if I take a vector here and a vector here and I add them, I now left the shaded region. So if I were to cook up an example of a set which is closed under scaling but not addition, how would we define this subset of R2? I would say it's all vectors in R2 such that, how do you characterize that? Okay.
They're either both positive or
Both negative. Exactly. And we're going to simply say that what we're saying is that the product is not negative, right? Negative times negative is positive. It's okay if you're. Okay, so clearly, if you take such an animal, right, and so we take a vector W, so we know that A times B is not 0, not negative. You take scalar, you scale. how do we know whether this is in W or not? How do we check? Well, to qualify, the product of the entries have to be positive, right? So let's check. And we get K times A times K times B. It's K squared times AB. Now, what do we know about K squared? It's a number squared cannot be negative. We know that A times B, because by virtue of belonging to W here, A times B is non-negative. Therefore, this whole product is non-negative. So indeed, this vector is in W. Okay, so W is closed under scaling. However, think of a counterexample like 1, 0, 0, 1. Keep it simple. These are both vectors in W, right? The product of the entries is not negative. It's 0, but that's okay. You add these up. Oops, what did I? Oh, yeah, sorry. There you go. Is that right? 1, 0? Yeah, that's what I drew. You add these up, you get 1, negative 1. This is no longer in W, clearly, because 1 times negative 1 is negative. So this is not closed under addition. Therefore, W cannot be a subspace. It's not a vector space in its own right. About matrices. And we said that matrices form this set of n by n matrices are vector space without proving it. It's just going down the list of axioms to see that they hold. So if we consider, say, symmetric matrices, right? So symmetric matrices, n by n matrices. So this is this W. It's the set of all matrices and set of n by n matrices, right? So you have these square matrices and some of them are symmetric, such that A transpose looks like. These are a set of symmetric matrices, n by n matrices. So is this set closed under a standard matrix addition? You take two matrices, which are symmetric, they're W. So we know that A transposes A, we know that B transposes B. If I add A with B, do I get something symmetric? Well, let's check. A plus B transposed, these properties of transposes. A and B are symmetric, so A transposes A, B transposes B. So A plus B transposed is equal to A plus B, therefore A plus B is symmetric. It is in the collection of symmetric matrices. So this set is closed under addition. And scaling, yeah. Right, you take a scalar K, take a symmetric matrix A. Is it in W? Well, of course it is, right? Because you transpose this animal, you get transpose of a number is just that number, A transpose, and A is symmetric, so A transpose is A. So K times A transposed is equal to itself, it's symmetric. So that's an example of a subspace which consists of matrices. What about something that's not a subspace? Right, so consider, again, square matrices. Square matrices. And define W to be the set of all such matrices such that A times X equals 0 has only the trivial solution. So there's just one solution to this homogeneous equation, namely X must be 0. So X equals 0 is only solution. Okay, so is this closed under addition or scaling? Well, neither one. Okay, so if we have a square matrix where we only have a trivial solution to the homogeneous equation, what is true about this square matrix? It must have a inverse, right? It must be invertible, right? So if the only solution to the trivial equation is 0, this means that A is invertible. So the question of whether adding two such matrices gives you another such matrix reduces to the question of asking whether if you add two invertible matrices you necessarily get an invertible matrix. So can you think of a counterexample, right, which shows if you, well, there you go. This is an invertible matrix. If you have this times unknowns equals the 0 vector, this homogeneous equation, you only have one solution. This must be 0. This is another invertible matrix. And the only solution to this equation is the trivial one. If I add these two matrices, do I get something that's invertible? No. Okay. So a counterexample, I can take two invertible matrices, add them, the result I get is not necessarily invertible, right? It's not invertible here. So W is not closed under addition. What about, even scaling this is not even closed under scaling, right? Because if I scale a matrix, which is invertible, right? How can I make it not invertible? What would I have to scale by? Remember, scalars could be positive, 0, or negative, right? Well, in this case, it's the 0 case that shows us that it's not closed under scaling. The 0 scalar times any matrix is the 0 matrix. And if you have 0 times X equals 0, you have non-trivial solutions. Okay? So this is not closed under scaling. Okay, what else did we say we're going to talk about? Just subspaces. So.
It's almost worth linear combination.
Yeah, we have like 2 minutes, so. Does anybody know what a Fourier series is? Have you heard of it? No? Well, anyway, I won't go into it. It's there's a very important vector space, which is the set of sines and cosines that look like this. Sines and cosines. Okay, n is an integer. And this set is an important vector space because you can write functions as combinations of these. Anyway, but I won't get into it.
What's it called?
So, yeah. If you're into engineering or communications. I guess that's it. I mean, I kind of cheated you out of some important stuff like span and null space. But so maybe, okay, what's a null space of a matrix? I'll quickly define it. The null space, if you have A times X equals 0, homogeneous, right? The system. The null space of that matrix is defined as the solutions to this equation. So it's, all the vectors X in the domain of, such that A times X is 0. So it's just the solution, the set of all solutions to this system. The null space of the matrix is a subspace. And how would you show that? So the null space of the matrix A is a subspace. Should at least get that much. Well, to show that it is, we show that, of course, X is part of a larger vector space, right? It's part of like Euclidean vector space. So it's a subset. First of all, is the null space non-empty? Because if it's empty, we can't really talk about it being a subspace. This is non-empty, right? Because the null space always contains X equals 0. So the null space is not empty. There's always that one trivial solution to this equation. And then maybe I should write the words null space. How about that? That sometimes helps. Okay. Well, then I show closures, the closure property. So closure under addition. Okay. So how would I prove that? Well, I will take two solutions to this homogeneous equation, i.e. two elements in the null space of our matrix. And I want to check whether if you add those, you get something that's in the null space. And how do we check? Well, this sum is in the null space. If A times that sum gives me the 0 vector, right? Then that's a solution to the homogeneous equation. But then we have the matrix multiplication is linear, so AX plus AY. And then because X is in the null space, A times X is the 0 vector, A times Y is the 0 vector. So indeed, X plus Y is a solution to the homogeneous equation here. So this is in the null space. So we have closure under addition. So the null space is closed under addition. Take two vectors in the null space, add them, you're still in the null space. And it's also closed under scaling. Right? So if you take scalar k, you have k times, then you have a solution to the homogeneous equation. Kx is in null space again. Because matrix A times Kx by linearity you get the 0 vector. So the null space is closed under addition and scaling, therefore it's a subspace. The null space of the matrix is a subspace. It's an important thing. There it is. Okay. Make sure to sign in if you haven't.